All right, so in this final segment of lecture 25, I would like to just kind of informally discuss these two results that they list at the end of section 33 in the book, which I think are pretty interesting, and they're a cool look into what you might learn about if you pursue functional analysis a bit more. So they have to do with what we can say in situations where functions may be converging to a limit, a sequence of functions might be converging to a limit pointwise, but not necessarily uniformly, right? So we've seen that if Fn converge to F uniformly, and the Fn and F are all integrable, then the integrals of Fn from, let's say, a to b, so this is like on an interval ab, then these integrals converge to the integral from a to b of f, right? That was something that we actually proved a while ago. And the gist of the proof there was that, we make Fn minus f be less than like epsilon over b minus a, right? So that way, if you integrate, sort of the total error is bounded by, b minus a times epsilon over b minus a. So yeah, that's the situation for uniform convergence. But there are still situations where Fn converges to F pointwise, but not uniformly, but still that the integrals are forced to converge to the integral of F. So that's kind of what this theorem here deals with. So this is the dominated convergence theorem. So suppose Fn is a sequence of functions converging pointwise to F on AB, where Fn and F are integrable, so all the Fn, right, and F are integrable if there exists some m. I don't know why they say greater than, I mean, whatever. I guess it's equivalent either way. M greater than 0 such that f of x is, or sorry, Fn of x is less than or equal to m for all n, and for all x in AB, then the integrals are forced to converge. So I think this is actually there's a very easy way to understand this. Okay, hold on. Yeah. Yeah. So I think when I first learned this, for some reason, I didn't really, I think I didn't really grasp this, but it's actually, it's surprisingly intuitive, okay? Because let me draw you a picture of the sort of canonical situation in which, or the classic situation where Fn might be converging to F pointwise, but the integrals don't converge. Okay, so I'm going to draw this diagram here. Okay, yeah, so here you can see, let's say this is F1, F2, F3, F4, F5, and so on, right? We've actually, I mean, it's not too hard to write down a formula for a sequence of functions that looks almost exactly like this. And you can arrange for the integrals of each function to be 1, right? But actually, these functions end up converging to 0 pointwise on this interval, because even though like the peak of the function is getting taller and taller, if you fix your attention on any point, eventually that peak gets further to the right of that point that you're looking at, and it keeps going, and then eventually the value of f at the point you're looking at will eventually be like approach 0. Okay, so fn actually goes to 0 pointwise, but the integrals can all be, you can fix them to all be 1. And the only way that's possible is that basically the area, right, the area gets concentrated near x equals 1, right? The maximum value of f must grow unboundedly for this to happen, right? It has to, because the spike gets narrower, right? The spike gets narrower, so it must get taller, right? To keep the same area. Like this spike, because it's getting squished further and further close to 1, it has to get narrower and narrower, but it has to get taller and taller at the same time to make sure that the areas stay the same. So dominated convergence kind of says like, okay, we're going to force an upper limit on all of these fn's, right? So if the convergence is dominated, all fn must stay below this line, right? So you eventually you can't have the fn's, like you can't have the areas like getting concentrated near a certain point, because fn is forced to stay below this line. So the spike can't get like tall enough to keep the area being the same. Okay, that's the gist of, informally, that's kind of the idea of what's going on. Of course, in the actual statement of the theorem, the hypotheses are only that fn and f are integrable, right? So fn and f may not even be continuous, right? So in this picture, for example, all of them are continuous, so it's easier to visualize. But it's a little bit more nuanced to actually prove this theorem. But this is really the heart of the idea of the proof, I think. It's just that, as the convergence, progresses further and further, that the places where the value, let's say fn minus f, right? We're looking at fn minus f, so that converges to 0 pointwise. Then the places where the value of that function is allowed to be large get smaller and smaller, so the total area is sort of like proportional to like the amount of the interval that you're integrating on, where the value is large, times like m, basically. That's like an upper bound, right? So that upper bound tends towards 0 as the convergence progresses. That's one way of thinking about it, at least. So anyway, that's dominated convergence. There's another kind of related result, which is the monotone convergence theorem. So this is 33.12. So suppose fn is a sequence of integrable functions on AB such that f1 of x less than or equal to f2 of x less than or equal to so on. for all x in AB, and suppose Fn goes to F pointwise on AB, where F is integrable on AB, then again, the integrals have to converge. So the limit as n goes to infinity, the integral from a to b of Fn is the integral from a to b of F. Okay, and this follows from, so the monotone convergence follows from the dominated convergence because, so like the picture here is like you have, you know, here's like F1, maybe, or actually better yet, okay, let me redraw this. Say, so maybe here is F1, and then like here's F2, here's F3, here's F4, right? So on. So, you know, each function is greater than or equal to the previous one at every point, right? And then maybe, you know, there's a bunch more, and then there's some kind of, you know, F that they converge to. So by picking a lower bound on F1 and upper bound on F, right? F sits above all of them, and F1 sits below all of them. So just picking an upper bound on F and a lower bound on F1 gives us a uniform. So we get a uniform bound on the absolute value of Fn of x for all n and for all x in A, B. And so then use the dominated convergence theorem with that bound, right? So, and the only reason we even have to pick the lower bound on F1 is just because like F1, if we just pick an upper bound on, if we want an upper bound on the absolute values of Fn, right? F1 might randomly be like a huge negative, like it could be like hugely negative or something like that. So it might actually have bigger absolute value than F, even though the functions like increase, you know, the values of the functions increase. That doesn't mean that F1 doesn't have a bigger absolute value than F of x, right? So, but by picking lower bounds here and upper bound, and the reason that they have to be bounded, right, is because they're assumed to be integrable, right? So F1 is integrable means F1 is bounded. F is integrable, that means F is bounded, right? Because we haven't defined integrability for unbounded functions, even though you can. That's improper. That would be improper integrals, which we're actually not going to cover. But for our purposes, integrability, you know, includes boundedness as a hypothesis. So by picking these bounds, then you can end up applying the dominated convergence theorem. So, you know, oops, yeah. All right, so that does it for lecture 25. So we just have one more lecture, which is about the fundamental theorem of calculus. So thanks for watching.